The dream has one big problem. Welcome to Unbox the World, where we explore the most incredible machines shaping the future of flight. Flying cars are no longer just science fiction. One looks like a personal flying race car. The other looks like a compact electric air taxi from Japan. The Jetson ONE promises single-seat personal flight with 8 electric motors and no runway. The SKYDRIVE SD-05 is built as a 3-seat electric flying vehicle designed for short urban trips. Both are real, both are electric, both take off vertically, but they share one massive problem. They still cannot fly very long. The Jetson ONE flies for about 20 minutes. SKYDRIVE targets short-range flights of roughly 9 to 25 miles or 15 to 40 kilometers. So why is electric vertical flight still so limited? Why can electric cars drive hundreds of miles, while small flying vehicles often measure endurance in minutes? And can this problem actually be solved? This is not just a comparison between two futuristic aircraft. This is the real engineering battle behind the flying car dream. The Jetson ONE, a flying machine built for one person. The Jetson ONE is one of the most viral personal flying vehicles in the world. At first glance, it looks like a Formula One race car that lost its wheels and gained 8 electric rotors. There is no enclosed passenger cabin. The pilot sits inside an open protective frame, wearing a helmet and harness, surrounded by electric propulsion units. It is not trying to be a family aircraft. It is not trying to replace an airline, and it is not designed to carry 4 people across a city. It is a single-seat personal eVTOL built for short recreational flights. And that is what makes it so fascinating. The Jetson ONE is small enough to feel personal, but serious enough to look like a real aircraft. It has 8 electric motors. It uses a lightweight structure made from aluminum and composite materials. It is controlled with a joystick, and its published performance numbers sound simple, but they reveal the entire challenge of electric flight. The Jetson ONE has an approximate flight time of 20 minutes. Its top-level flight speed is software limited to 63 miles per hour, or 102 kilometers per hour. Its maximum pilot weight is 210 pounds, or 95 kilograms, and its aircraft mass, including batteries, is approximately 253 pounds, or 115 kilograms. That means the aircraft itself is extremely light compared with a conventional helicopter. But even with that lightweight design, it still flies for only about 20 minutes. And this is where the dream meets physics. A flying vehicle does not roll on the ground. It has to lift its entire weight into the air and keep it there. Every second it hovers, the motors must fight gravity. Every pound matters. The pilot matters. The frame matters. The batteries matter. The motors matter. Even the landing gear, wiring, and safety systems matter. On the ground, extra battery weight can help an electric car drive farther. But in the air, extra battery weight is also extra mass that must be lifted. That is the cruel trade-off. Add more batteries and you add more energy, but you also add more weight. And now the aircraft needs more power just to lift the extra batteries. This is why small eVTOLs face a much harder problem than electric cars. A car can carry a heavy battery pack and still roll efficiently on roads. A vertical aircraft has to lift the battery pack, the pilot, the structure, and the safety systems into the air, all at once. The Jetson ONE is impressive because it makes this possible in a compact personal vehicle. But the 20-minute flight time shows how difficult the next step will be. To become more than a thrilling recreational machine, personal eVTOLs must answer one question. Can they fly long enough to be truly useful? SKYDRIVE SD-05, Japan's compact flying taxi approach. The SKYDRIVE SD-05 takes a very different approach. Where the Jetson ONE is a one-person open-frame flying machine, SKYDRIVE is designed more like a small air taxi. It has a cabin. It is intended to carry 3 people, 1 pilot and 2 passengers. It uses 12 electric motors and rotors. Its maximum takeoff weight is approximately 3,100 pounds, or 1,400 kilograms. Its maximum cruise speed is approximately 62 miles per hour, or 100 kilometers per hour. And its published target range is approximately 9 to 25 miles, or 15 to 40 kilometers. That makes the SD-05 a much larger and more ambitious aircraft than the Jetson ONE. It is not just lifting one person. It must carry a pilot, passengers, the cabin structure, landing gear, batteries, rotor systems, flight control computers, and the safety architecture needed for a passenger aircraft. That adds comfort, but it also adds weight. And weight is the enemy of electric vertical flight. SKYDRIVE is not designed to fly across an entire country. It is designed for short-distance air mobility, airport connections, resort routes, short urban hops, sightseeing flights, and places where direct air travel can save time, even over a relatively short distance. This is important because many people misunderstand early flying taxis. They imagine a vehicle that replaces a car completely, but the first realistic eVTOL aircraft may not replace the car. They may replace specific painful trips. A congested airport transfer, a route across water, a trip around a mountain or bay, a short premium journey where the ground route takes much longer than the straight line distance. In that kind of mission, a 15 to 40 kilometer range may actually be useful, but it is still limited. And if SKYDRIVE wants to carry paying passengers, it cannot simply use every bit of battery power and hope to land perfectly. Aircraft need margins. They need reserves. They need safe diversion planning. They need enough energy for unexpected conditions. Wind, route changes, holding time, delays, emergency landing options. So when an eVTOL advertises a range number, the real commercial route may need to be shorter than the theoretical maximum. That is the difference between a specification sheet and real aviation. The SD-05 shows how electric air taxis may begin. Short routes, careful planning, controlled environments, and missions where speed over the ground matters more than total distance. But if the Jetson ONE and SKYDRIVE both face short flight time, the question becomes obvious. Why do electric flying vehicles struggle so much with endurance? The real enemy is not the motor. It is energy density. Electric motors are not the problem. In fact, electric motors are one of the strongest parts of the eVTOL idea. They are compact. They respond quickly. They have fewer moving parts than combustion engines. They can be distributed around the aircraft. And they make it possible to build vehicles with many smaller rotors instead of one large rotor system. That is why eVTOL aircraft can look so different from helicopters. Jetson uses 8 electric motors. SKYDRIVE uses 12. Joby uses 6 tilting propellers. Volocopter uses 18 rotors. Whisk uses multiple propellers on a winged autonomous aircraft. Electric motors make distributed propulsion possible, but the weak point is not the motor. It is the energy storage. Aviation has relied on liquid fuel for more than a century because fuel is incredibly energy dense. A small amount of aviation fuel contains a huge amount of usable energy. Batteries are improving, but they are still much heavier than liquid fuel for the same amount of stored energy. That is why a small gasoline aircraft can fly for hours, while many battery electric vertical aircraft fly for minutes. The issue becomes even more severe in hover. In forward flight, an airplane wing carries the aircraft efficiently, but during vertical takeoff and landing, the rotors must generate enough thrust to lift the entire aircraft. That requires enormous power. The more time an aircraft spends hovering, the more battery energy it burns. This is why aircraft design matters so much. A pure multicopter is simple, but it is not very efficient for long-distance travel. It must use rotor thrust to support its weight for the entire flight. A winged eVTOL can take off vertically, transition to forward flight, and then let the wing do much of the lifting. That is far more efficient. But it also adds complexity, tilting rotors, control transitions, wings, larger structure, more certification requirements. The Jetson ONE works around the problem by staying extremely light and limiting its mission to one person in short flights. SKYDRIVE works around the problem by focusing on short urban routes and compact passenger operations. Neither has completely defeated the battery problem. They are working around it. And this is the heart of the flying car challenge. The technology is real, but the mission must match the energy available. If the mission is too ambitious, the aircraft becomes too heavy. If the aircraft becomes too heavy, it needs more power. If it needs more power, it needs more battery. And if it needs more battery, it becomes even heavier. That loop is what every eVTOL company is trying to escape. Why adding more batteries does not simply fix the problem. The most obvious solution sounds simple. If flight time is too short, add more batteries. But in aviation, that idea quickly becomes dangerous. A battery is not just stored energy, it is also weight. If you double the battery size, you do not simply double the flight time, you increase the aircraft's mass. Now the motors must work harder, the frame may need to be stronger, the landing gear may need to handle more weight, the control system must manage a heavier aircraft, and the aircraft may need bigger rotors or more powerful motors. That can create a chain reaction. More battery means more weight means more structure means more weight means more power demand. At some point, adding batteries gives diminishing returns. The aircraft becomes heavier faster than its useful endurance improves. This is why eVTOL designers fight for every pound. A lighter seat matters. A lighter canopy matters. A lighter rotor arm matters. A lighter landing gear matters. A lighter battery enclosure matters. Even paint, wiring, and displays matter. The Jetson ONE shows one extreme of this thinking. It strips the personal aircraft down to the essentials. One pilot, open frame, no passenger cabin, no luxury interior, no baggage space, no long-range mission. That is how it reaches ultralight style personal flight. SKYDRIVE has a harder job. It needs a cabin, passengers, more structure, and a more public transportation image. So its aircraft must balance range, comfort, safety, payload, and regulatory approval. That is why flying taxi development is much slower than social media makes it appear. The aircraft is not just a drone scaled up for humans. Scaling up changes everything. A small drone can fly for a short time because it carries a tiny payload and operates with limited risk. A passenger eVTOL carries human beings. The aircraft must be redundant. It must tolerate failures. It must be stable. It must be tested. It must be certifiable. And all of those requirements add weight. So the question is not simply, can we add more batteries? The real question is, can we increase useful flight time without making the aircraft too heavy to fly efficiently? That is much harder. The difference between a personal flyer and a flying taxi. Jetson ONE and SKYDRIVE are both electric vertical flying machines, but they belong to very different worlds. The Jetson ONE is a personal, recreational aircraft. It is designed around one pilot and a short flight experience. Its goal is not to carry a family across a city. Its goal is to make personal flight feel simple, thrilling, and physically possible. The pilot sits in the aircraft. The aircraft responds directly. The flight is short. The experience is emotional. It is closer to an extreme recreational vehicle than a public transportation system. SKYDRIVE is aiming at something broader. It wants to become part of urban or regional air mobility. That means passengers, routes, certification, operating partners, vertiports, and public trust. A flying taxi cannot just be exciting. It must be reliable. It must fly scheduled missions. It must meet regulatory standards. It must operate safely around buildings, other aircraft, and people on the ground. It must land where passengers can actually use it, and it must do all of that at a price people are willing to pay. That is why the same battery limitation feels different for each machine. For Jetson ONE, 20 minutes can be enough for a thrilling personal flight. For a flying taxi, 20 minutes may be barely enough for a short commercial route, once reserves and operating margins are included. A recreational pilot may accept short endurance. A commercial operator needs predictable route economics. That is a major difference. A personal eVTOL can sell freedom. An air taxi must sell time savings. If the aircraft only saves 5 minutes, the business case may fail. If it saves an hour of traffic, the aircraft becomes valuable. This is why early eVTOL routes will likely be carefully selected. They will not fly everywhere. They will fly where the geography makes sense. Across water, between airport and downtown, between resorts and remote destinations, across congested cities where the ground route is painfully slow. This is how short-range eVTOL aircraft may become useful before battery technology becomes perfect. They do not need to replace every car. They only need to beat the worst trips. Can flight time be increased? So can flight time actually be increased? Yes, but not by one magic solution. There are several possible paths. The first is better batteries. If battery energy density improves significantly, eVTOL aircraft can carry more usable energy without gaining as much weight. That would increase range and endurance directly. But aviation cannot adopt new battery technology casually. The cells must be safe. They must handle high discharge rates. They must tolerate vibration, heat, cold, and repeated cycling. They must be protected from thermal runaway, and they must satisfy regulators. So even if a battery breakthrough appears in a lab, it can take years before it becomes a certified aircraft battery system. The second path is better aerodynamics. A winged eVTOL can fly more efficiently than a multicopter during cruise. That is why many larger air taxi designs use fixed wings. The aircraft may burn a lot of energy during vertical takeoff, but once it transitions to forward flight, the wing carries the weight far more efficiently. For a personal aircraft like Jetson ONE, adding wings would change the entire design. It would make the vehicle larger, more complex, and less like the compact flying machine that made it famous. For SKYDRIVE, future versions may continue improving aerodynamic efficiency, but its compact urban mission still limits how large and winged the aircraft can become. The third path is reducing hover time. Every second spent hovering burns energy quickly. If an eVTOL can take off, transition efficiently, and land without long hover periods, it saves power. This is one reason vertiport operations must be carefully designed. An aircraft waiting in the air for a landing pad wastes energy. In commercial service, scheduling and air traffic management become part of the endurance problem. The fourth path is lighter structure. Carbon composites, optimized frames, lighter avionics, and better manufacturing can all help. But weight reduction becomes harder over time. The first cuts are easy. After that, every pound becomes expensive. The fifth path is hybrid propulsion. A hybrid electric aircraft can use fuel to extend range, while still using electric propulsion for vertical lift or distributed control. This could dramatically improve endurance, but it also adds engines, fuel systems, emissions, maintenance, and complexity. It is no longer a pure zero-emission electric aircraft, and that may change the public image. The sixth path is battery swapping. For short-range aircraft, swapping battery packs between flights may be faster than waiting for a full charge. But aircraft batteries are heavy, expensive, and safety critical. A swapping system must be precise, reliable, inspected, and integrated into aircraft maintenance procedures. For personal flying machines, removable batteries are attractive. For commercial flying taxis, battery logistics could become a major operational challenge. So yes, flight time can improve, but every solution creates a new trade-off. Better batteries require safety validation. Wings increase efficiency but add size and complexity. Hybrid systems extend range but reduce simplicity. Battery swapping reduces turnaround time but adds infrastructure. The future will not be one perfect solution. It will be a combination of better batteries, smarter aircraft design, lighter materials, better routes, and more realistic expectations. Why the first flying cars will not be like cars. There is another problem hidden inside the phrase, flying car. A car can stop almost anywhere. It can wait in traffic. It can pull over. It can refuel quickly. It can carry heavy batteries and still be useful. A flying vehicle cannot behave the same way. It needs safe takeoff and landing zones. It needs airspace management. It needs weather limits. It needs emergency procedures. It needs maintenance standards. It needs trained operators. And it needs clear rules for where it can fly. This is why the first successful flying vehicles may not feel like cars at all. They may feel more like aviation services. You may not own one. You may book a seat. You may fly from one approved vertiport to another. The route may be short, controlled, and carefully monitored. The aircraft may operate only in good weather, and the price may be premium at first. That does not make the technology a failure. It makes it aviation. Jetson ONE is different because it is aimed at personal recreational flying. It can exist as a flying experience for trained owners in suitable locations. But urban passenger eVTOLs like SKYDRIVE must integrate into a transportation system. That means rules, infrastructure, and public acceptance. The dream of stepping into a flying car in your driveway and landing on any rooftop is still far away. The realistic future begins smaller, short flights, specific routes, carefully managed operations, limited payload, and gradual improvement as batteries and regulation mature. This may disappoint people expecting instant science fiction, but it is exactly how aviation usually evolves. The first version is limited. The second version improves. The third version becomes practical. And only after years of operation does the technology begin to feel normal. Jetson ONE versus SKYDRIVE. Which one makes more sense? So which aircraft makes more sense? The answer depends on the mission. If the goal is personal excitement, the Jetson ONE is more compelling. It is smaller. It is simpler. It gives one person the sensation of flying directly. It does not need to solve the entire problem of urban air mobility. It only needs to provide a safe, controlled, short-duration personal flight experience. For that mission, 20 minutes may be acceptable. A recreational flight does not need to cross a city. It only needs to deliver something almost nobody has ever experienced before: direct, personal, electric flight. But if the goal is public transportation, SKYDRIVE is the more relevant aircraft. It carries multiple people. It has a cabin. It is designed around certification and commercial use. It is more likely to operate as part of a future air mobility network. But that mission is much harder. A flying taxi must be more than exciting. It must be safe, repeatable, certifiable, and economically useful. So Jetson ONE may reach personal owners faster. SKYDRIVE may take longer, but its mission could affect more people if it succeeds. One is freedom. The other is transportation. One is like a flying motorcycle. The other is like an early electric taxi for the sky. Both are limited by battery technology. Both reveal the promise and frustration of eVTOL aviation. And both show why the flying car revolution will not arrive as one sudden moment. It will arrive in categories. First, personal flyers. Then, short commercial routes. Then, larger urban air mobility networks. And eventually, perhaps, aircraft that can fly farther, carry more, and become ordinary enough that people stop calling them science fiction. The future is real, but the battery still decides everything. The Jetson ONE and SKYDRIVE prove that the flying car dream is no longer only a fantasy. One person can already sit inside a personal electric flying machine. A Japanese company is building a compact three-seat eVTOL for short urban mobility. The aircraft are real. The rotors spin, the batteries work, the flight computers stabilize the aircraft, and the public is finally seeing vehicles that look like they came from the future. But the future still has a limit. For now, that limit is flight time. The Jetson ONE flies for about 20 minutes. SKYDRIVE is designed for short-range trips measured in miles, not cross-country journeys. And every electric vertical aircraft must fight the same physics. Batteries are heavy. Hovering consumes huge power. Extra range adds weight. Passenger comfort adds weight. Safety systems add weight. And aviation does not forgive careless design. So can we increase flight times? Yes. Better batteries will help. Better aerodynamics will help. Lighter materials will help. Smarter routes will help. And hybrid systems may help certain aircraft fly much farther. But the first generation of flying cars will not be unlimited machines. They will be short-range, carefully operated, mission-specific aircraft. And that may be enough. Because every aviation revolution begins with a machine that looks limited at first. The Wright Flyer barely stayed in the air. Early helicopters were unstable and difficult. The first electric cars had short range. And today's eVTOLs are facing their own first-generation limitation: endurance. But if companies like Jetson and SKYDRIVE can keep improving, the question may not be whether flying cars are possible. The real question is, how long before they can fly far enough to become part of everyday life? Which aircraft would you choose? The single-seat Jetson ONE or the three-seat SKYDRIVE? Tell us in the comments below. And subscribe to Unbox the World for more incredible aircraft, futuristic vehicles, electric aviation, flying cars, eVTOL technology, and the machines changing how humans move through the world. This is Unbox the World. We do not just show you the future, we open it. Thanks for watching, and we will see you in the next video.